Efficiency is how much bang you get for the buck. In other words, how much of the work, how much of the energy, how much of the power that we're putting in goes into doing something useful, and how much of it is wasted, usually as heat and sound. The symbol for efficiency is that letter there. It's an eta for those of you who are scorekeeping at home. It's sort of like a lowercase curvy n with a droopy tail. Although I usually just write EFF. I didn't know that was the symbol for efficiency until a few years ago. I didn't know it had its own symbol, but I know that some of you like to nerd out with Greek letters, so, there you go. So if you write EFF period, I'll figure out that that's efficiency. Units, well, it's usually measured as a percentage. What's the equation? Efficiency is work out divided by work in, and then times 100% to make it a percent. Or power out divided by power in, and then times 100% to make it a percent. Or, really, Duick? Energy out divided by energy in, and then times 100% to make it a percent. Morning. Of course, there's probably an easier version of the equation, and there is. What's the easier version? This is how I remember if I'm doing efficiency. I know that efficiency is always the smaller number on top divided by the bigger number on the bottom, and then times 100%. Another late person. The only problem with this is you need to make sure the units match. Hannah, don't go joules divided by watts is the common error. Because energy is measured in joules, work is measured in joules, we're good there. Power is measured in watts, so don't go watts over joules or joules over watts. Efficiency is always less than 100% unless you plan on winning a Nobel Prize. If you could design something that was more than 100% efficient, the fancy phrase for that is more efficient than unity, we say, you would have what we call a perpetual energy, a perpetual motion machine. It would violate the laws of physics. But if there was such a machine, even with our current level of technology, if you gave me a free, unlimited source of energy, Alexis, I could engineer my way out of almost all the world problems just with our current level of technology. Climate change, we've got free energy, so we can easily come up with ways to modulate heat and cool things down. Food shortages, let's run lights all night. We can double our crop production because we can use sunlights to have the crops grow at nighttime. Free energy. There's a lot you could do with free energy, but the universe, Nick, just doesn't work that way. The reason I say that is in your future, there is a question when we get to power, when we get to electricity. The problem with electricity, what do you call the thing that you plug something into? An outlet. The power coming into your device is coming from an outlet. It's very easy for you to get confused. Is that the power out or the power in? And I know there's a question in the future, just the way it's worded. I'll have a whole bunch of kids telling me, this is 140% efficient. And I will just laugh at you. No, it's not. Can't be. Okay. Another late person. So, a typical household light bulb transforms energy at the rate of 60 watts. What was 1 watt? It was a joule per second. So a typical light bulb, the incandescent ones, not the LED ones, transforms energy into light and heat at 60 joules per second. But most of the energy is transformed into heat instead of light. Only about 57 watts are used as heat. Only about 3 watts are used as light. An incandescent light bulb is only about 5% efficient. A kettle might transform electrical energy into heat at the rate of 1500 watts. The power rating of an electrical appliance is usually printed somewhere on the appliance. And as a rule of thumb, the more heat an object is moving around, the more heat an appliance is moving around, the higher its wattage. Example 1. A 255 kilogram mass is being lifted. I would probably mentally underline the word lifted, because if I'm thinking about how much work, it's going to be mgh. Straight up at a constant speed, that might also be fairly handy by an electric motor. It takes the motor 4 seconds to lift the mass to a height of 12.5 meters. Okay, cool. Hannah, what does A want me to find? So work equals force times distance, but when we're lifting, I think we've agreed as a shorthand it's mgh, because you're doing the force that you're lifting with is exactly the same size as gravity pulling down, especially here because it does say constant speed, so I know the forces must be, I'm looking for where this starts letter B, balanced. So it's going to be 255 times 9.8, not negative because we're in Scalarville, times 12.5 meters. I still haven't got my calculator working after the Windows update, so you'll have to just start typing on your own. I'm trying to find a good substitute. I'll do this on my actual calculator. Do y'all get 3062.5? No? Oh, no, totally wrong. I missed a digit. How about 31,237.5? I'm going to write down all the digits and then I'll round off. So 31237.5 to 3 sig figs, 31,200 joules. Okay. B. Find the required power. Ooh, Camille, how do I find power? Camille, back row, Camille. So check on your formula sheet. How do I find power? This was last day's lesson, so if you don't have your fingerprint, that's fine. Okay. There's actually 2 versions of power. Let's see if we can use this first one. Do I know the work? Just calculated it. Did they give me a time? Okay, then we'll use this one. By the way, I would have no problem going straight to part B without asking part A. Is that all right? It's going to be 31237.5 divided by 4. Answer button divided by 4. And now I get 7809.375. And I'll write that as 7,810. Camille, power is measured in watt? Power is measured in watt? Thank you. Okay. Other Camille, what's C asking me to find? So how am I going to find efficiency? Well, the first thing I notice is they're giving me an answer in watts, kilowatts, but 12 kilowatts, 12,000 watts. I can do that conversion in my head. So I'm going to compare wattages. So it's going to be power out divided by power in. It's going to be the smaller number divided by the bigger number. So I know the 7,809.375 is going to go on the top, and the 12,000 is going to go on the bottom, and then times 100%. Sorry? Question. That's how I knew to use the watts and not the work, not the joules. So on my calculator, oh, this drives me crazy not being able to show you. You'll get 65% efficient, 65.1% efficient. Okay. Where does the rest of the power go? Or where did the rest of the work go? Heat. A lot of it sound. A lot of it. In fact, the fact that this efficiency is that, probably this is not an electric motor. This is probably some kind of internal combustion motor, although internal combustion motors are usually even worse. Electric motors are pretty efficient. They don't generate much heat. Example 2, a girl pushes a box along the floor for a distance of 4 meters. Yeah, turn the page. The coefficient of kinetic friction, mu, is 0.33. She then lifts the box straight up 1.2 meters. What's the minimum amount of work she has done? Donald, what's this question asking me to find?
The minimum amount of
work. I said minimum. It's possible she might have done more. We're assuming she's doing bare minimum, and I'll explain to you kind of why in a bit. I think she's doing 2 things. I think the total work is going to be the work done while pushing the box and the work done while lifting the box. Now, normally I would freak out on you if it was kinematics. I would say, wait a minute, that's horizontal and that's vertical, and they cannot go in the same equation, but we're in Scalarville, so oh yes, they can. How do I find work? Work was equal to what times what? So I think I'm going to say the force of pushing times the distance plus, how do I find the work in lifting? Yep, mgh. How hard was she pushing? Did they tell me? If you were I'll say it, a bad physics student, you might be tempted to say, isn't that the force of pushing? 3, because it's got a newtons. Is that the pushing force? I don't think so. I see Ronan doing this. I don't know what that means. Oh, I thought you were trying to hint something. Oh, my bad. I thought you were smarter than you were. I'll never make that mistake again. Sure. What's the, yeah, I think this is mg, 300. How hard is she pushing? Well, do you see a coefficient of friction mentioned, Prab? I think this is a job for a free body diagram. See how I kind of put that together? I'm gonna do it maybe right over here in the margin. What are the forces acting on this object? Get the obvious one. Hello, get the obvious one. Can we have more than one person say that? Get the obvious one, everybody. How big exactly as a number this time? Okay, so I'm gonna go mg, and that's 300. And I guess there's a normal force. I don't see any hint of a hill here, so I'll assume the normal force is equal to mg. What else? Which way? Okay. What else? Okay, how big? This is why I said minimum amount of work. She could be pushing harder than friction, I don't know, but they said minimum, so I'm going to assume that she is exactly matching friction. In other words, the box is not speeding up or slowing down, it's traveling how? Constant velocity, constant speed. If I had said constant speed, then we could have assumed minimum work and I wouldn't need to make this assumption. I just said we'll assume the minimum work. So, I don't know, F push. Oh, but look. I don't know the force the same size as F push. What? Friction. Friction is what times what? Okay, so now we can say mu times the normal force. Wait. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. What? Okay, so I'm going to go mu times 300 times d plus 300 times h. Okay. So the total amount of work done is going to be, what's mu? I don't know. What's mu with you? What's mu? 0.33 times 300 times distance up 4 meters plus 300 times 1.2. What do we get? Max, what'd you get? 756 units, Max? Joules. Okay. Supposing that she expended 1,200 joules of energy, how efficient is this? Well, efficiency is going to be, work that we got out divided by work that we put in times 100%. Again, it's a little tough to see what was the work out, what was the work in. Efficiency is going to be the smaller number divided by the bigger number. Efficiency is going to be 756 divided by, what did I say, 1,200? And I get 63% efficient. What happened to the other 37%? That energy left her body, probably lots of it in the form of heat. Maybe she was sweating, giving off body heat. Also, some of it would have been used up by friction, heating up the floor. Okay. Not all of it went into moving this object. Mr. Dewick, is it possible that instead of giving us the bigger number and the smaller number and asking us to find the efficiency, you could give us the efficiency and then either the bigger number or the smaller number and ask us to find the other number? Yep. On a stair climber at the gym, a 58 kilogram person lifts their center of mass up 18 centimeters. Nice try, Mr. Dewick. Do we do physics with centimeters? No. 18 centimeters is how many meters? My physics 11s just wrote their kinematics test, and there was a question on there that asked them to go from centimeters to meters. And the number of kids that told me that it was 18 centimeters was 1,800 meters drove me crazy. Because you've all held a ruler, I assume, like 18 centimeters? You're telling me that's 1,800 meters? Anyways, I'll make fun of those kids when I go over the test. Okay. If they take 500 steps in 10 minutes, nice try. 10 minutes, how many seconds, please, in your head? No. 600? 60 seconds in 1 minute, 600 seconds in 10 minutes, times by 60. And their muscles are 20% efficient. Okay, here we go. Alessio, what's A asking me to find? Is it asking me to find work? So, no. What's it asking me to find? Read it again. The rate at which the person does work. So what is it asking me to find? What? Someone said it. And then they didn't say it again. Wow. Power. Power is the rate at which we do work. This is asking me to find power. Camille, what's the equation for power? It's on your sheet. Yeah, you don't have to memorize it if you don't want to, but have it handy, right? Work over time. Did they give me a time in this question? Okay, I'm on the right track here. In fact, I'm pretty sure it's going to be over 600. Work. Ooh, I probably should have mentally underlined the word lifts. It's going to be MGH. What's M? G, 9.8. What's H? I'll give you a hint. It's not 0.18. It's not 500. Steps? We do physics with steps, do we? Caden, what? The total height this person lifts their body through must be 0.18 meters for each step, but they do 500 of them. Even though they're staying in one place, they're lifting themselves up. Okay. All over 600. What do you get? You get 85.26. Watts. 500 steps in 600 seconds, that's a little less than 1 step per second. Not a heavy workout if you think about it on a stair climber. This person is not doing a lot of energy per second. Okay. Now, if you've ever used an exercise device, often they will try and tell you how much energy you've burned. It'll actually say in calories, or if it's really high-tech in joules or something like that. A total garbage. Those numbers are totally garbage because, first of all, for them to figure out how much power you've generated, they need your mass. I don't think most of those machines ask you to enter your mass. Some do. The better ones will actually ask you to enter your mass in. Okay, but let's keep going. The rate at which the person uses food energy. What's this asking me to find? What piece of information haven't I used yet? Efficiency. You know what? I think this is asking me to find the power that this person put into the exercise. This here is the power the person got out of the exercise. I think what we're going to go with is efficiency is going to be power out divided by power in. Technically times 100%, but instead of doing that, I'm going to convert the 20% back to a decimal as 0.2. Well, first of all, I want to get the power in by itself. Where is it right now? On the... Wait a minute. I think this is the same as power in equals power out divided by efficiency. That's a terrible eta. Efficiency. I think it's going to be 85.26 divided by 0.2. See, here's the problem. People have different levels of human efficiency. If you're in good shape, you're probably more efficient because this workout wouldn't cause you to sweat as much. It wouldn't cause your body to heat up as much. It wouldn't cause your body to burn as many calories. It's ironic that if you're in better shape, you don't burn as many calories doing this. If you're in lousier shape, you're going to be huffing and puffing 10 steps in. You're really going to be sweating. Your body's going to be burning and giving off a lot of heat. You're going to be burning more calories. So those exercise machines, when they tell you how much quote-unquote calories you burn, that's total nonsense. It's a best guess average maybe, for what it's worth. What'd you get? units. So although this person on the exercise machine put out 85.26 joules per second of work, their body was burning 426 joules per second of energy to do this exercise. The good news is that usually means, especially, this is why they always want you to get your heart rate up. Once you get your heart rate up and you're sweating, you're burning way more calories than just the exercise itself is demanding. Little food science for you there. Example 4. An internal combustion engine, a gasoline engine, is approximately 18% efficient. Internal combustion engines are terribly inefficient. Do they give off a lot of heat? A great deal of heat. Can you hear them from a long distance away? That's wasted energy. Sound is a form of energy. They're terribly inefficient. This is why even if you have a hybrid which has a small internal combustion engine in it, the fact that you're getting most of your power and your drive from a much more efficient electrical engine, you're still coming out way ahead. Electrical engines are far more efficient. So this means that only 18% of the chemical energy used to operate the motor is converted into forward motion. The other 72% is wasted. If a 200 horsepower engine is used for 2 hours, A, how many watts is this motor rated for? How much motion energy in joules does it produce? And how much energy is wasted? Okay. I guess we're going to convert horsepower to watts for part A. Whenever I do a conversion, the first thing that I do is I write down what they gave me. Where am I going to put horsepower in my conversion factor? On the top or on the bottom if I want it to cancel out? Bottom. So watts is going to go on the top, and I guess it's 750 watts is 1 horsepower, and now I know I'll times by 750, not divide. And I get 150,000 watts. Ooh. Nick, what's B asking me to find? In what? In what? No, in brackets. In what? Look at the units. So what's this question? What do we measure in joules? What's this question asked me to find? Work. Okay. Don't write this down. Look up. My first thought, Nick, would be, well, work equals force times distance. Don't write that down. Do you see a force or a distance anywhere in this question? And this is how my brain would handle this. Like, okay, try that first. I don't see newtons anywhere. Do you? I don't see the word lift, which would allow me to do MGH. Do you? I don't see a distance in meters. Do you? Okay. Work is also the area under a force versus distance graph. Did they give you a graph? Okay. Then I might say, what did I find in part A? Does power have work in it? Oh, what's the equation for power? I don't know why I'm picking on you, but it's just going to be a thing today. So this is my thought process. My first thought would have been, I wouldn't have written all that down, but I would have said, well, force times, no graph. Oh, maybe I found part A for a reason. Power is work over time. How would I get work by itself? Work is going to be power times time. It's going to be 150,000 times 2. Or, here's it. Why can't, well, oh, I'm going to have to convert the 2 to seconds. Does anybody remember how many seconds there are in an hour? Some of you might have memorized it last year out of laziness. Okay. 60 times 60. So it's going to be this number times 2 times 3,600 I'm getting a fairly big number. In fact, I think I'm going to write this in scientific notation. The amount of work done is 1.08 times 10 to the 9. Is that right? Nick, what are the units for work? That's how I knew that this was asking me work. Okay. That's how much energy we got out. Or is it? Is this right? This here is the total energy used up. This is the work we put in. It's not what we're going to get out. Most of this is going to be wasted. How efficient is this motor? 18%, which would be as a decimal 0.18, but 18%. We want work out. So efficiency is work out divided by work in. Smaller number divided by the bigger number. We want the smaller number. This is how much energy is being used grand total, but most of this is not going into making the car go forwards. How would I get the work out by itself? It's going to be 0.18 times 1.08 times 10 to the 9th. So times 0.18. And I get 1.944 the work that we get out is 1.944 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 joules. Adam, what C you want me to find? Sorry? Yeah, question? How am I going to figure out how much energy is wasted? I could either go total energy minus this number, or I could find 72% of this number, because that's going to be how much is wasted, since 18% went into useful energy. So I'm going to do it subtracting. So what did I call this? Work wasted is going to be 1.08 times 10 to the 9th minus 1.944 times 10 to the 8th. 1.08 times 10 to the 9th minus answer button. And I get that we have wasted 8.856 times 10 to the 8th joules. Electric cars, or perhaps hydrogen fuel cell cars, are the future, but electric motors are far, far more efficient than internal combustion engines. Okay. What's your homework? So you can try number 1. You can try number 2. 3 is good. 4 is good. I'll probably assign most of these because these are easier Physics 11 questions. 5 is good. 6 is good. 7 is good. Turn the page, please. 8 is good, 9 is good, 10 is good, 11 is good. Can we do 12? It's accelerated from there to there with an acceleration of blah, blah, blah. What's the net force? The what force? The net force. Sure, you can go MA, that works. Distance you can find. Sure, 12 is a nice review of a little bit of everything in Physics 11. I'll skip 13. 14 is good, 15 is good. So basically I skip 13.